Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from integral inequalities. So here once again we have a very important problem from integral inequalities. So here we have to show that the absolute value of the integral 0 to 1 square root of x square plus x dx is less than or equal to square root of 3 over 2, right? So here without calculating the value of the integral, we have to show that the absolute value of this integral is less than or equal to square root of 3 over 2, or in other words we can say that the absolute value of this integral, it doesn't exceed over square root of 3 over 2, right? So let us start. So let us call this integral as I, right? So we have I is equal to 0 to 1, and the integrand is the square root of x square plus x dx. So we have to now show that the mod of this integral, that is mod of I, is less than or equal to square root of 3 over 2. So now to prove this inequality, here we'll make use of one important result from definite integrals, right? See, if we have two functions, say f of x and g of x, which are integrable and continuous in the closed interval a comma b, right? And if f of x and g of x are continuous function in the closed interval a comma b, and the square of this function f of x is also integrable, and similarly the square of this function g of x is also integrable in the interval a comma b, then we have a very nice result which is known as Cauchy-Squarz inequality, right? So the Cauchy-Squarz inequality states that the absolute value of the integral, that is a to b of f times g dx, right? The absolute value of the integral of the product of the function f and g from a to b is less than or equal to square root of the product of these two integrals. That is, the first one is from a to b, and here we have f square dx, and here we have a to b g square dx, right? So this inequality is known as Cauchy-Squarz inequality, and here the absolute value of this integral a to b f times g is less than or equal to the square root of the product of the integral, that is f square dx from a to b and g square dx from a to b. So we'll apply this result to prove this inequality. So now let us concentrate on this integrand. So here we have square root of x square plus x, which can be written as x times x plus 1, and here we have dx, right? So we can further write this integrand as square root of x times square root of x plus 1 dx. So why we have expressed square root of x square plus x like this? Because we can take this function as f of x, or simply f, and this function as g of x. So we can take f of x as square root of x and g of x as square root of x plus 1, right? So now we can apply this inequality to these two functions, that is f and g. So now we can write the absolute value of the integral, that is a to b. A is 0 and b is 1. So we have 0 to 1, f is square root of x, g is square root of x plus 1, and here we have dx. So this is less than or equal to the square root of the first integral, that is from 0 to 1, and here we have f square, right? So square of f is equal to x, right? So here we have simply x dx, and the second one is g square dx. So the square of the function g of x is x plus 1, right? So here we have 0 to 1 x plus 1, and this is dx. So now let us separately calculate these two integral. Let us call it as I1, this is I2. So I1 is integral 0 to 1 x dx. So this is x square over 2. The limits are from 0 to 1. So we have half minus 0, that is equal to half, right? And here I2 is also a simple integral. So we have I2 as 0 to 1 x plus 1 dx. So this is x square over 2 plus x. The integral of x plus 1 is x square over 2 plus x, and limits are from 0 to 1. So when we substitute the limits and we'll take the difference, we have half plus 1 minus 0 plus 0, that is 0, right? So this is 3 over 2, right? So now this inequality can be rewritten as mod of this integral. This integral is our I. So mod of I is less than or equal to square root of I1 and I2, right? So this is square root of I1 is half, and I2 is 3 over 2. So now mod of I is less than or equal to square root of half multiplied with 3 by 2. So this is square root of 3 over 4, that is square root of 3 over 2. The square root of 4 is 2, right? So this is how we have obtained this inequality, that is the absolute value of the integral I is less than or equal to square root of 3 divided by 2, right? So viewers, this is how, by making use of this important integral inequality, we can solve these kind of integral inequalities. Hello viewers, in today's class we are going to discuss another important problem from integral inequalities. And in this class we are going to use a very important result from definite integrals, which can be used to solve or to prove this inequality, right? So here we have to show that the mod of, or the absolute value of the integral 0 to 1 square root of 1 plus x square times 1 plus x raised to 4 is less than or equal to 2 times square root of 10 divided by 5, right? So we'll see a new inequality or a new result, which is also known as Cauchy-Squarge inequality, which will be used to prove this integral inequality, right? So let us first see the statement of Cauchy-Squarge inequality. So Cauchy-Squarge inequality states that if we have two functions, say f of x and g of x, right, and these two functions are integrable and continuous in the interval a comma b, right? We can also write it as x greater than or equal to b and less than or equal to a and b, right? Okay. So now if fx and gx are two continuous functions and integrable functions, and if the square of this function, that is f square x and g square x, are also integrable, right? So if the square of this function and the square of this function are also integrable in the interval a comma b, then the Cauchy-Squarge inequality states that the absolute value of the integral a to b and f times g, that is here we are using the notation simply f for f of x and g for g of x, right? So the absolute value of this integral is less than or equal to the square root of the product of these two integrals, that is a to b f square dx, and then we have the integral a to b, and here we have g square dx, right? So this inequality is known as Cauchy-Squarge inequality, and this inequality plays a vital role in proving a lot of other integral inequalities. So let us first take this integral as I, which is inside the mod function symbol, right? So we can take I is equal to 0 to 1 square root of 1 plus x square, and here we have 1 plus x raised to 4, and this is dx, right? Now let us express this integral like this, that is a to b f times g dx. So for this, what we will do, see, a is 0 and b is equal to 1, right? So lower limit is 0, upper limit is 1. So we can now write this integrand as 0 to 1. Here we have a square root of 1 plus x square, and then we can write it as 1 plus x raised to 4 dx, right? So now this function may be taken as the function f or f of x, right? And this function may be treated as g of x. So now we have an integral a to b f times g, that is the product of f and g. So f is square root of 1 plus x square, and g is the square root of 1 plus x raised to 4. So now let us calculate this integral, right? So let us take this integral as I1. So I1 is integral a to b. Here a is 0, b is 1. So we have 0 to 1 and f square. So f square is square root of 1 plus x square whole square, and here we have dx. So this is 0 to 1, and simply we can write 1 plus x square because the square root get cancelled with this square, and we have simply 1 plus x square dx, right? Now we have a simple integral. The integral of 1 plus x square is simply x plus x cube over 3. Limits are from 0 to 1. Now substituting the limits and taking the difference, we have 1 plus 1 cube over 3 and minus, then we'll take 0. So this is 0 plus 0, and here we have 1 plus 1 over 3, that is 3 plus 1 over 3, that is 4 over 3, right? Now let us take this integral as I2. So I2 can be written as integral a to b. A is 0, b is 1, and g square. So here gx is square root of 1 plus x raised to 4. This is square, this is dx, and now we have 0 to 1, and square root sign it get cancelled with this square, so we have 1 plus x raised to 4 dx. So this is x. Integral of 1 plus x raised to 4 is x plus x raised to 5 over 5, and limits are from 0 to 1. Now we can substitute the limit. So we have 1 plus 1 raised to 5 over 5 minus 0 plus 0, right? So this is 1 plus 1 over 5, that is 5 plus 1 over 5, that is 6 over 5, right? So the value of I1 is 4 over 3 and I2 is 6 over 5. So now this Cauchy-Squarz inequality, it assumes the form, if we take this integral a to b f g dx as I, because I is our this integral, so we have mod of I less than or equal to, we have square root of I1. Here we have I1 and then we have I2, right? So this is square root of I1. I1 is 4 over 3, I2 is 6 over 5, right? So now we can simplify this expression. So we have here square root of, this is 3 to the 6, this is 2 4 the 8, 8 over square root of 8 over 5. So now mod of I is less than or equal to square root of 8 over 5. This can be written as 2 root 2. Square root of 8 is 2 times square root of 2 divided by square root of 5, and we can rationalize it. So we have here square root of 5 over square root of 5. So this is 2 times, this is 2 5s are 10. So this is square root of 10 over 5, right? And this is our desired inequality, right? Because I is this integral. So mod of I is less than or equal to 2 times square root of 10 over 5, right? So viewers, this is how by making use of this important inequality, which is known as Cauchy-Squarz inequality, we can prove these kind of integral inequalities.